In this video, we're going to talk about complexity of algorithms. In particular, we're going to focus on time complexity. So what we'll be doing is kind of looking at the worst case time amount on an algorithm. How much time would potentially be spent? Now, the word time does not necessarily mean minutes, right? What I'll really be looking at is tasks. How many tasks will be completed? And I'll be looking really for the maximum amount. All right. So let's kind of step through this. It really is kind of better by example. And we're going to be referring to some algorithms we saw in 3.1. So let's look at the time complexity for finding the maximum element in a finite sequence. So this is the algorithm, and the idea was you start with the first element, right? And then you, which they call a sub 1, the first term in the sequence, and then you keep comparing those to the other terms. So what we have is kind of two steps that happen when we approach a term. So first step is we compare the terms, and then we determine whether or not there is another term after we're done. Determine the next term. So the idea is if you have this like list of terms, right? Like here, let me just write a list. 1, 2, 3, 4, 5. Okay, great. So I have this sequence of terms, and the idea is when I start with the max, right? The max is the first term. And then I compare that max to the second term. And I'm like, okay, which one's bigger? So if the second term happens to be bigger, the comparison's done. And then the question becomes, do I move on? Is there another term to worry about? So that's like the second task that occurs, okay? So this needs to happen every time we take and do a comparison for all of the terms. So we would kind of think of this as a step that occurs. And in this step, we have two transactions. Two transactions. Okay, so how many times is that going to happen? Well, we're calling the number of terms here, they're n terms, right? N terms, because a sub n is the last one. So there's n terms. And since the first one, that doesn't really happen with the first one, because the first one has to be chosen to be our maximum to start. That means that this transaction happens n minus 1 times. Okay. So what we have then right now is 2 times n minus 1 transactions. That's how many transactions have occurred. All right. Then we do have an additional step. So we have like a final step that kind of happens, and this tends to happen in all of them, this like final step where you kind of exit the loop, or you decide whether or not you have to keep going. Or is there more? the program kind of has to figure out if there's more that it has to do. So that actually adds an additional step. All right. So that means, I'm going to do this in green just because I unfortunately have to write a little bit big, that we have 2 times n minus 1 plus 1 steps, or if you like do the math, 2n minus 1 transactions. Okay. Now, if I wanted to use the notation that we did in the last section of big theta, that means that our theta is of the nth, is of the order for n, because it's n is the polynomial leading coefficient in degree. Okay, so that would be how many transactions there are, and then the book does take an extra step to determine that that means that our big theta is of the order n. All right. Okay, so let's look at another one. Determine the time complexity for the linear search algorithm. So this is the one where you're searching not for the maximum, but for a specific term. Okay, so you're searching for a specific term. So you have this term you're after, right? This term you're trying to find, and we call the term X, right? So that's the name of the term, right? X is this magic term that we're trying to find here. Okay, so either we find X or we don't. So we're trying to look for X, and what happens is we do this comparison to see if the term is X. So one thing that happens is we check each term to see if it is X. Then when we're done checking a term, right? We start with the first term, we check, is it X? Then we move to the next term. So that's the second step. We see again if there is another term. How did I word that just a second ago? Determine the next term. Determine if there is another term. So you have to figure out if you have more terms to compare it to. So again, just like in the last one, we have two steps. But the difference this time is that we're going to do this comparison also with the very first term. So there's actually n times that we're going to do these two steps. Okay, so 2n is where we're at right now in number of transactions. And just like the last one, there is an additional step that's like that final step to see if we've reached the end of the list. Okay, but there is one more extra step on this one, and that is if it happens to not be in this list, if X can't be found, then there's also another possible step of saying that there is X is not found. So there's actually another one. So another additional step if X isn't on the list. So this adds two more steps to the 2n that have already occurred. So we have 2n plus 1 tasks that we're going to be performing. So again, our big theta would be of n, of order n. My big theta looks kind of sad, sorry. That's supposed to be that little marking in there. It's kind of like an H, right? But it's not supposed to be fully an H. Oh, well, it's fine. I did the best I could. Okay, now this one's a little bit of a different question. And it's actually a bit loaded when they ask for the average case performance. In fact, it even says that. It's actually difficult to find it, but it's possible to find it for the linear search algorithm, the one we just did. Okay, before we do that, we need a piece of information. Okay, in your book on page 176, and this was section 2.4, I believe, there is a table called table 2. And that table gives this sum. The sum as k goes from 1 to n of k, which by the way, would mean that we're basically just adding the integers, positive integers, starting at 1. And that ends up being this. Now, we are actually going to show this in chapter 5. So we will prove this, but for right now, we're just going to believe that this is true, that if you were to add 1 to n and just keep going, all those numbers, 1, 2, 3, 4, 5, all the way up to n, it's going to end up being the same thing as taking n times n plus 1 and dividing it by 2. All right. Now, before we get to that, we're going to use this little fact here. Okay, this is a little factoid that we're going to use to help us. All right, so here's what we're going to do. We just discovered that that 2n plus 2 is the maximum amount of steps we're going to take. Okay, the maximum amount of steps. Now, we're going to go ahead and assume that we do have the X term in the list. Okay, so we're going to make the assumption X is in the sequence, the A sub 1, A sub 2, A sub 3, that sequence of terms that we're checking, which means that we don't have the extra last step that we had right here. This step is no longer needed. So that means that we have 2n plus 1 tasks to complete. Okay, so suppose the very first term is the term we're looking for. That means then that n would be 1, and that means we did 3 tasks. That means we first compared it, we checked to see if we needed to move on in the list, and then we jumped out of the loop. So there's 3 tasks to complete if the first term happens to be the term we're looking for. Then, if it's the second term, that ends up being 5 tasks to complete. 2 additional tasks are going to occur. Basically, by the way, all I'm doing is I'm plugging in 1 for n for the first term. Oh, thank you. Thank you for not selecting my highlighter. There we go. 1 for n for the first term, right? First term, n equals 1. And then n equals 2. So I'm plugging it in there and I'm getting odd numbers. That's what's going to happen. I'm just going to keep getting odd numbers all the way out until 2n plus 1, the nth term. All right. And this would be all the possible tasks that will occur. And if I divide that by n terms, that would be the average we're looking for. Okay, now here's where we get super fancy. 3 happens to be 2 plus 1. I'm kind of using this formula here and putting that as the 2 and the plus 1. Okay. 5 happens to be 4 plus 1. And 7 happens to be 6 plus 1. So I'm taking each of these and I'm writing them as a plus 1. All right. And that keeps going until I get to the last term, which is 2n plus 1. And it makes sense. 2n is even. All right. So here's what I'm going to do. I'm going to take all of the plus 1s and put them together. And this is all divided by n. All right. So I'm going to deal with that in a second. I'm going to divide by n in a second. So here, I'm just going to take that away for a second, just because I don't have a lot of space. So I'm just working with adding these together. And then when I'm done, I'm going to divide them by n. Okay. So I'm going to take all of the even numbers and put them together all the way to 2n. And then all of the 1s I'm going to put together. So my next question is, how many 1s are there? Or there would be n of them, right? Because there's n terms. So this is going to just be n. This I can factor out of 2. Why would I want to do that? So that I can use that fact that I wrote above. This fact right here, that if you have the sum from 1 to n, we have a formula for that. All right, so here we go. We're going to take that. So we're going to come back here now. We're going to 3 plus 5 here, dot, dot, dot. I'm not going to bother with the 7. Divided by n is going to equal, okay. So this 1 plus 2 plus 3, this right here, I can now substitute this formula in for this n times n plus 1, all divided by 2, plus this n right here. This n is right there, okay, divided by the n that's here in this denominator right there. Okay, I hope we followed everything. Those 2's cancel. Boop, boop. And we're left with n times n plus 1 plus n all over n. So we can actually cancel an n everywhere. This is going to become a 1 though. So I'm left with n plus 1 or n plus 2. There it is. There's the average. Ah, we did it. That was a lot of work. All right. Let's do another example. The binary search algorithm. So this is the one, the algorithm where you split it into two, like you'd half the list and you'd split it into two to do the search. I'm going to write the example that we kind of used when we did this to help us understand these steps, okay? Because it's a little bit complicated. So here we go. I think the first example we had was we had looked at 1, 2, 3, 5, 6, 7, 8, 10, 12, 13, 15, 16, 18, 19, 20, and 22. And what you do is you split it in half, right? You like cut it in half. That's the halfway point. And you look at them as two separate groups and you judge whether or not which group you're going to pull from. So the first example, I believe the number we were interested in finding was 19. Okay. So that was like the magic number we were looking for. So we would like do a comparison with these front two numbers here. And we'd say, okay, based on those two numbers, which list am I going to select to continue searching? And that would be the second list because 10 is clearly much smaller than the number we're searching for. So we're going to look at the second list because that list is the one that's going to be useful to us. So then we relist this 12, 13, 15, 16, and break it up again into two lists. So there's that kind of middle part, and then do the same comparison and then break it up again. And you keep doing this breakup thing until you find the number you're after. Okay, so here's the idea. All right. For simplicity's sake, I want to go ahead and assume that I have an even number of terms so that the list splits nicely. But I'm going to cheat, and I'm not just going to use 2n. I'm actually going to assume that n equals 2 to the k. I'll explain why that's allowed, why we are allowed to make that assumption, okay? But we're going to assume that we're working with 2 to the k. For us, in this particular example, there are 16 things we're looking at. So our k would be 4, just so we're clear, all right? Because 2 to the 4 is 16. Okay, so I'm going to make the assumption. Here, let me do this actually down below. Wow, it's not wanting to let me erase. There we go. All right. We're going to assume that n equals 2 to the k. All right, so here's what that does. That means right up here in this first line, I have 2 to the k elements. All right. And then I take half of the list. So if I divide this by 2, if I take 2 to the k and I divide it by 2, that gives me 2 to the k minus 1 because I'm subtracting a 2 out. Or there are k2s right here. And if I divide by 2, I remove one of those 2's. So I'm left with 2 to the k minus 1. Just so we're clear. All right, I'm going to write this down. If I divide this by 2, that's 2 to the 1, and you have to subtract the exponents. All right, just so we're clear. Great. So if I do that again, I'm having the list again. What's going to happen? I'm going to remove another 2. And this pattern is going to continue until I'm down to 2 terms. All right. So the question is, what's changing each time? And the answer is the exponents are decreasing by 1 every time. So whatever k is how many steps we're going to take. We have k steps that we're going to take here. All right. So I've just determined how many steps there are. So here's what happens on each step. So switching to red. No, I want to do green. On each step, 2 things happen. We check to see if there's an end of the list, if we keep going, and we're searching for our term. It's kind of the same 2 steps we've been doing in the last 2 examples. All right. We do have a final step. Where we're going to exit the loop and the potential that we can't find our term. Oh, for, sorry. Another for X. Wow, not on list. Okay, so not being able to find the term we're searching for. All right, so since we have K steps, and there's 2 steps every time, that's 2K. And this is an additional 2 steps at the very end. So we have 2K plus 2. All right, now that's not the final answer because K is something we introduced when we said let N equal 2K. Really, what we're saying, if you use a logarithm, is that K equals log base 2 of N. That's changing it to logarithmic form. So we can then instead use a logarithm to describe K so that it has an N instead. Now, a couple things that are a bit annoying. First thing, this, because we've introduced a logarithm and logs end up having the same order when we're working with big theta, we don't have to work with log base 2. We can just use the common log. In fact, the book just makes the leap of saying K equals log N, even though it's technically base 2. All right. So I plug that in over here for K. And that is the number of tasks. As theta, which I'll squeeze in here at the very bottom of the page, it's a logarithm of N. Okay, now, quick comment on why we are allowed to assume it is even. We can assume it's even because we are going for the maximum number of steps. If it's not even, we will end up being able to show that it's possible to compensate. All right. Now they chose 2 to the K on purpose, just so that they can introduce this notation in the end, this logarithmic notation. All right. But I'm not going to get too heavily into that. And you don't have to really worry about showing that. The problems that you'll be assigned won't really be doing this. This is kind of showing you how we look at tasks, all right, that are being completed. Okay, now we're going to take a break from that and we're going to talk about matrices. Technically, matrices was section 2.6, and we didn't cover it because we didn't need the whole section. We just need pieces. So I'm going to introduce the concept of matrices and the piece that we need for this section. Okay, so a matrix is a rectangular array of numbers. A matrix with m rows and n columns is called an m by n matrix. So the best way of thinking of a matrix, I like as a real world example, is the idea that maybe these are the numbers in a table of data. Okay, like we have this table of data. Here, I'm going to give an example and I'm going to erase this. But let's say I'm interested in students at OCCC. And I'm interested in where they live, what city they live in, and their age. So I have this table, all right, and this is, I'm not really going to write this out, where all the cities are possible. Okay, so here's Newport, here's Lincoln City, here's Depot Bay, and etc. Right? All the cities are listed out. And then we have age ranges. We're like, okay, 18 to 24, 25 to 35, whatever. Okay, all these age ranges. And then we have a bunch of data in here. Okay, there's 20 students that work here and 50 students that work here, and I mean that are in that group and so forth. All right, so we have this group of numbers. They can be represented by a matrix. All right, so that's a real world example of where we see matrices. This is literally data, tables of information. We're just getting rid of all the words and only looking at the numbers because, hey, that's what math people do. Okay, now, so that's an example of a matrix. Here's another example of a matrix. Let's say 1, 3, 5, 7, 9, 11. There's one. Okay, here's another one. 1, 5, 7, 8, 2, 3, 0, 4, 6. Great. There we go. three examples of matrices. Now, each matrix has rows. These are the rows, and columns. These are the columns. So this starting matrix has 2 rows, 2 columns. So it's a 2 by 2 matrix. Okay. This matrix has 1, 2, 3 rows and 2 columns. So it's a 3 by 2 matrix. Erase all these little tick marks marks I'm making all over the place here. So this last one would be a 3 by 3, 3 rows, 3 columns. Great. Okay, now this is going to introduce a notation that will be used. And it's the idea that we can label the terms of a matrix based on their location of row and column. So like right here, this one, this term is in the first row, second column. And I see that because the 1 is first, that's the row, that's the column. First row, second column. So here, coming up here in this matrix right here, this matrix, the term that's in first row, second column, boop, it's this 5. Okay. Right here, the term that's in 3, 1. Third row, first column, boop. Oh, 5 again. That was totally by chance. I don't know. Apparently I like 5. Okay, here where's 5 in this one? Well, that would be second row. Oops, I'm supposed to do that in blue. Second row, second column. There we go. Okay, so it's a way of labeling where an element is on the matrix or where a term is on the matrix. Okay. All right, and then real quick, this is what we call the nth column, which I could, if I wanted to, write its own matrix. A1n, 2n, 3n, you keep going all the way down to mn. Here, let me boop, make it long enough. I can make a matrix like that. That matrix, by the way, would be a m by 1. 1 column, m rows. All right. And that works for the rows as well, right? So this is the mth row. And I could do a matrix for that. M1, M2, dot, 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 Mn. So this would be a 1 by n matrix. So it's possible to just look at a row or column of information. All right. Now, definition. So this is how we can represent a matrix without writing out a bunch of crap. We call it A sub ij. That is a J. I'm sorry, it's kind of hard to see on my thing because the Word document is upset that I have that notation. But that's saying that we have a matrix that has all of these elements in it. They tell us it's an m by n matrix, and we have a B. So we have 2 matrices. Both of them are m by n, and we can add them together. And the way you add them together is you add their corresponding elements. So add wow, that's not how you spell corresponding. Corresponding elements or terms. We'll say terms. It's quicker. So let's say I want to add these 2 matrices together. That means I'm going to add first row, first column, first row, first column. And that's going to add up to be 4. Here, I'm going to have to make it a little bigger because I write, unfortunately, bigger than the computer can type. And it doesn't want to let me erase or move. There we go. Okay. And then I can add second row, first column. That's going to give me 3. And then I can do third row, first column. And that's going to add up to 2. All right. I think you get the idea, right? Go ahead and continue adding them up. I'm going to write the answers down. And then you can check. Make sure you match. That's a 3. All right. So exciting. So adding is boring. Great. But they have to match. We have to have the same dimensions, same row, same column in order to add them. Okay. Multiplication is much more complicated. All right, much more complicated. With multiplication, we're going to be multiplying the rows of the first matrix times the columns of the second matrix. And really what we're doing is we're adding the corresponding elements. I'm sorry, we're multiplying the corresponding elements and then adding them together. It's actually a little bit easier for me to show you. Okay, so here we go. Let's look at this example here. Oh, sorry. So I'm going to take the first row and I'm going to multiply it by the corresponding elements in the first column. So I'm going to write this out too. I'm going to show the work. So that means I'm going to do 1 times 3, which is 3, plus 0 times 1. Here, actually, I'll actually write the multiplying out. 3, 0 times 1, plus -1 times -1. That's the first term in the matrix, which when you work it out is going to come out to 3. That's a 0. That's a 1. It's going to come out to 4. So the first term is going to come out to 4 in the multiplication. Okay, second term. Let me erase, please. Let me erase. There you go. I'm going to do first row, second column. First row, second column. All right. So first row, second column, that means it's going to go in the first row, second column spot. So 4 times 1 plus 0 times -3 plus -1 times 1. And let's see, that's going to work out to be 4. That's a 0 minus 1 is 3. So that'll go here in the next spot. All right, next column. 1 times -1, that's going to be the first one. And is it okay if I'm going to go ahead and start just actually multiplying? So 1 times -1 is -1 plus 0 plus -2, which is going to come out to -3. All right, next one. So now I'm going to start second row, first column. So that's going to be 2 times 3, which is 6, plus 2 times 1 is 2, plus -3 times -1 is 3, which is going to be 11. Now I'm going to go to the next column. 4 times 2 is 8. Oops. Plus 2 times -3 is -6. Plus -3 times -1 is -3. So I'm getting -1 for that term. And now third column. So that's going to be 2 times -1 is -2. 2 times 0 is 0. And -3 times 2 is -6. So that's going to be -8. All right. Try the last row yourself. Like pause the video, try it. But I'm going to work it out and you can see. Okay, so this is final row, first column. So that's going to be 9 plus 4 plus 0, which is 13. Then we'll have next column, 12 plus -12 plus 0. So that's just going to come out to 0. And then last column, I will have -3 plus 0 plus 0. Don't you love 0? I do. There you go. There's our answer. So you multiply the corresponding elements and then add them together. All right. Matching them up and then multiplying them. So we're matching this up. Oops. Yeah, oh, that worked. We're matching this up with this. And then we do, oops, now it's mad because I touched the screen. I'm sorry. Stop it. Stop being mad. All right, I'm moving on. Moving on. Let's try it again. Trying it again. Oh, it got so mad at me. I'm sorry. Hold on. I got to try to allow me to get back in here. Okay, so excuse me, I literally had to close out the program. I had to rewrite it, and I apologize. Probably looks a little bit different than what I just wrote a second ago, but that was the only way I could get it to keep going. So I'm sorry for that. All right, we're gonna move on and try another matrix multiplication. Now it'll actually let me. All right, so again, we're gonna do first row, first column. Same idea, but this time I'm going to go ahead and I'm not going to show all the multiplying. I'm going to go ahead and just say the multiplying and then actually do it. Okay, so here we go. We're going to do 2 times 4, which is 8. And then -4 times -1 is 4. So 8 plus 4 is 12. That's the first term. All right, and then we're going to go first row, second column now. So that's going to be 2 times 1, which is 2. Plus -4 times 3 is -12. So that comes out to -10. All right. Now, second row, first column. So that's going to be 12 times, or I'm sorry, 12 minus 3, which is 9. And then we're going to have 3 plus 3, which is 6. I'm sorry. Yeah, nope. 3 plus 9. 3 plus 9, right? Because 3 times 1 is 3. 3 times 3 is 9. So 3 plus 9 is 12. Cool. All right. Then we're going to do last row, first column. All right. So that's going to be 4 and 0. So that's 4. And then we're going to have 1 and 0, which is 1. All right, so there we go. Now, do I know the dimensions of the answer? Like the matrix that we get as a result? The answer is yes, and it's based on the dimensions of what we're working with. So right here, this first matrix, this is a 3 by 2 matrix, all right? 3 rows, 2 columns. The second matrix is 2 by 2. So first of all, these two have to match. In order to multiply, they have to match. All right. In fact, let's come up here. So up here, we're doing a 3 by 3 and another 3 by 3. And these two, boop, they match. So we're good to go. We can multiply them. They have to match. If they don't match, we can't multiply them. All right. And here's what's cool. These two, the outer two, actually make up the dimensions of the answer. So the answer is a 3 by 2. And it is. I have 3 rows, 2 columns. So up here, the result is a 3 by 3, which is what I had. Right? Based on the outer two. All right. Let's do this again. Okay, so this time we have a 2 by 2 and a 2 by 2, which is going to work because the inner two match. And we're going to get a 2 by 2 result, right? So let's do it. Let's do the multiplying. If you want to pause the video and try it yourself, I'd encourage you to do that just to get some practice in. Okay, so let's do this. 1 times 2 plus 1 times 1, that's going to be 3. Then 1 times 1 is 1, plus 1 is 2. And then that's going to be 2 times 2, which is 4, plus 1 is 5. And then 2 times 1 is 2, plus 1, which is 3 again. All right, so that's my answer. I got 3, 5, 2, 3. 2 by 2 is my answer. Now, really quick, I want to show you something. Let's assume this is matrix A and this is matrix B. What if we swap them? What if we do the reverse? B times A. 2, 1, 1, 1. 1, 1, 2, 1. I don't know why all of a sudden I decided I wanted to do the ones fancy, but I did. Okay. Fancy ones. There we go. Let's multiply them and see if we get something different. So let's see. 2 times 1 is 2. 2 times 1 again is, so that's a 4. All right, we're already different. It's going to give us a different result. Okay, so first row, second column now. So that's going to be 2 plus 1 is 3. And then 1 plus 2 is 3 again, and then 1 plus 1 is 2. All right, so if we switch the multiplication, that means that matrix multiplication is not commutative. That's the phrase we use in math when we are allowed to reverse the order. You cannot reverse the order with matrix multiplication and get the same result. You get two different results. And in some cases, you can't reverse the order at all and actually multiply them. Like in our last example, you can't reverse the order of those matrices because then you would have a 2 by 2 and a 3 by 2, and these don't match. So you can't even multiply them. It won't work. All right, so there we go. That's matrices. That's all you needed from matrices. And what they do is they use this to talk about another algorithm, and they want to talk about the complexity of the matrix multiplication and creating an algorithm for matrix multiplication. Now, I have to admit to you, I stared at this a while. This one actually took me a little bit of time. So the way the algorithm is working, where I got a little bit confused was right here, this step, where they are defining C sub ij to be our result, but then they use C sub ij, I'm sorry, I said G and I meant J, C sub ij in the actual addition. And that just weirded me out because matrix addition, we talked about the definition of that before we even did all these multiplying up here, right there. Matrix addition is an addition with A's and B's, right? But there's no C, it's equal to C. So I got really weirded out by that. In fact, I called my father, who does programming, to ask, and then he kind of helped me out. We actually discussed it. And here's the weird thing that made it a little bit weird. Right there. They actually set that equal to 0. So this is a way for the program to write an addition, a sum. It's a way for it to do a summation with this 0. Because apparently it doesn't have the feature of sum when we're writing in this pseudo coding language. Okay, so it confused me a little bit. We don't really need to focus on that to answer the next question, but I do want you to understand the algorithms, and I'm hoping that you understand them even better than I do. Okay, so here we go. How many additions of integers and multiplications of integers are used in the matrix multiplication algorithm to multiply two n by n matrices? Okay, so I want to kind of set this up with understanding what we're doing here. Okay, so an n by n matrix, let's look at a 2 by 2 matrix. Okay, 2 by 2. Here, I'm just going to call it 1, 2, 3, 4. Boring. Great. How many terms are there in this matrix? 4 terms, right? Well, that comes from squaring 2. 2 in the row, 2 in the column. So if I do a 3 by 3, 1, 2, 3, 4, 5, 6, 7, 8. There are 9 terms here, and that comes from doing 3 rows by 3 columns. So 3 squared. All right. And I'm bringing that up because if we're talking about n by n, that means n by n has n squared entries. Okay. There's n terms in that matrix. Okay. Every entry, I'm thinking that there may not be an E here in the word entry. I'm like all of a sudden questioning. That doesn't look right either. Okay, we're just gonna put it back. Sorry if I spelled that wrong. I'm so sorry. All right, I'm over it though. All right. Entries. Okay, so for every entry, all right, how many multiplications do we do, right? When we're doing these multiplying. So here, I'm going to go back up to our first one where we listed out all the multiplying and adding. Okay, so for the first term here, how many multiplications were performed? 3. 3 multiplications. Oops, that's not how you spell multiply. 3 multiplications and 2 additions. Same with this next term, 3 multiplications, 2 additions. So when you multiply the 2 by 2, you're doing 2 multiplications, 1 addition. So the number of multiplications relates to the dimension. So every entry has n multiplications. And then the addition, there is 1 less addition and n minus 1 additions. So if we have n squared entries and in every entry we have n multiplications, that means that we have n squared times n, or n cubed multiplications. And for the additions, we have n squared times n minus 1 additions. And there you go. That's how many. Okay, now I'm going to define this, and I'm not really going to discuss it much further than the definition, but a brute force algorithm is solving something in the most straightforward manner without taking advantage of any ideas that can make the algorithm more efficient. All right. We've actually used brute force algorithms in particular when we did the sequential search, the bubble sort, and the insertion sort. All right. And then the last thing I'm going to point out is table 1 that came out of here, which gives us the complexities in theta, big theta notation, and giving the terminology we use related to those complexities. So a lot of the complexities we saw were theta, a big theta of n. Those were linear complexities. We did see 1 logarithmic complexity, all right? But there's the listing of the terminology for complexities.